from introducing transfer functions given by capital H, which are in the S domain. Looking at an RC circuit as we did in the last video, we found that the transfer function is equal to this. And we know that S is the complex frequency, and as it tends towards infinity, the transfer function is equal to 0, and as it tends towards 1 divided by RC, the transfer function blows up. So these two cases will present information that we can look at to establish pole zero plots. And when the transfer function goes to 0, we call that a 0. Seems to make sense. And as the transfer function goes to infinity, positive or negative infinity, we call that a pole. Now if we look at the S-plane, we'll recall S is equal to sigma plus j omega. We have a real component and then a complex component. So we're going to have a real axis and an imaginary axis. Now breaking away from the RC circuit here, we represent our poles as x's and our zeros as o's. And whatever the value for S is, or either a pole or a 0, we simply fill that in on the S-plane. So to consider an example, let's look at the case where we have a transfer function given by S plus 3 divided by S plus 1 minus J3 times S plus 1 plus J3. So we get a 0 at S equals 3, and then we also get zeros at plus and minus infinity, as this denominator is similar to S squared. Now, if S is equal to minus 1 plus or minus J3, we simply get this denominator going to 0, so the transfer function blows up. So we can say that we have a few zeros and a few poles for this transfer function. So now if we take that over to the S-plane and plot that, you have a pole here, you have a pole here, and you have a 0 here. So if we look at this pole here, we have on the real plane, goes back minus 1, and then it goes up 3, which would give us our S equals minus 1 plus J3. Then down here, we would have minus 1 minus J3, and then here you would have S equal to minus 3. Now we didn't put the zeros for the infinities, often in case you might not see them on the pole 0 plot, because your plot would need to be quite large to express that, and what is the physical reality of having an infinite frequency to begin with. So if we consider an RLC series circuit, we simply get an output voltage following the same procedure from the last video, and we can get our transfer function. And this transfer function yields poles at S squared times L plus S times R plus 1 divided by C being equal to 0. You can use the good old quadratic formula to solve what S is equal for, and we get two values. Now, if you recall the circuit analysis for RLC circuits, this kind of looks like the condition for overdamping, underdamping, and critical damping. So we can have some relation to what we looked at in previous videos. But in general, we're concerned with the frequency response of a circuit. So we're going to say that S is equal to j omega instead of the sigma term here. And while the S-plane technique does have its value, and you can do interesting things with it, it's a little bit difficult to read. If we scroll back up here, where we looked at this example, we saw that we had 2 poles and a 0, but we can't really see what's going on in between there. We have no idea what the transfer function looks like at, say, S equals 1 plus J1. So that's kind of the limitation. It's good for pointing out the poles, good for pointing out the zeros. And if we actually plotted what S was, we get this complex surface. So if we look down here where we've now made a 3-dimensional plot, where we had the real axis, the imaginary axis, and then we have what S is. Sometimes you might see the magnitude of S instead. You can see we had these poles here. So where we have poles, we know that we're going to get these infinities that emerge. And S can be thought of as this complete blanket covering the entire surface. So it exists everywhere, but at certain points it blows up to infinities or we get zeros. And it doesn't always have to be flat. You can get wavy nature in there as well. But to determine what the nature of that complex sheet for S actually looks like, it's a little bit confusing. So pole 0 plots They're okay to use, serve some purposes, but we want to consider Bode plots, and Bode plots are going to give us a much better representation of the frequency response of a circuit.